So welcome back, everybody. I have three challenges with this talk because number one, it's statistics. Number two, we switched to R. And number three, it's sunny for the first time this week. So, but no, I think we have some interesting topics and concepts to discuss. And I think it also has some good connections to some of the other talks. So I think you'll see some similarities of the things that we're thinking about from the statistics side to some of the other talks about graphs and summary functions and things like that. So let's jump right into it. Just before I do, just to also make a little bit of a plug for a meeting that I'm organizing in Switzerland in the Italian part, a very beautiful area, all about benchmarking. So this is a little bit of an experiment on my side. People who know me know I do a lot of kind of benchmarking studies and so on. But I didn't know that I was able to attract a lot of people to come to a meeting about benchmarking. And so this is really in the context of genomics data analysis. And we have 11 keynotes, and we had a call late last fall, and we have about 20 contributed talks and about 25 posters. And if you're interested, please get in touch with me because there's a very specific registration system for this location that we're at. But I think here's just a really quick snapshot of some of the talk. So it's quite a broad kind of spectrum of computational benchmarks and tools for various types of data that some of which we're dealing with here. So okay, so just kind of where are we now? So I stole the slide from Helena a while ago, and there's nothing new here. So you've kind of seen different versions of all of this. I just want to just remind you that, well, there's maybe these two main streams of spatial data, spatial transcriptomics, but I'm also thinking here more broad, spatial omics, so also the protein measurements and so on, also multi-omics measurements. And we have these two spectrums, and this is going to be important later because this determines how we think about it in terms of statistical modeling and so on. And so roughly speaking, so you have this molecule level data, and these are typically targeted panels, although nowadays some of these panels are really large, getting to full genome. And if you're interested in single cell, well, you probably require some sort of segmentation. So it's more about kind of aggregating of signals. If you have the sequencing data, well, again, it sort of depends, but your analysis could be deconvolution, as it was discussed, or it could be aggregation, or as Naveed and Nicholas showed you, maybe there's kind of an intermediate kind of segmentation-free kinds of analysis, which I guess also can be applied to this type of data. So I think we know this, right? So this, we're sort of thinking of, the data sort of determines the different analyses that you can do or the different analysis streams. And so I want to take that and go one step further to think about statistics. And in statistics, there's, well, maybe two subfields that are maybe of interest here. There is so-called lattice data analysis. So you might have heard of this. And what lattice data analysis is where you have data on a lattice. So basically often a regular grid of points, but actually it doesn't have to be a regular grid. It can be just a fixed grid of points. So you have a fixed grid of points and you're making measurements, and maybe you're interested in things like autocorrelation and so on of that lattice using the locations of those points somehow in the analysis. So that's one subfield, and the other is point pattern analysis. So I'll get into all the formal definitions of this in a minute, but in short, we're thinking about points in maybe a random pattern, and there's a model behind that pattern that controls certain aspects, maybe about clustering or interactions between different cell types and so on. So there are some possibilities there, but we'll get to that in a second. I want to say, well, again, the data sort of determines how you can represent this in terms of a statistical analysis. And so it's a little bit the same as what we saw before, sequencing-based, imaging-based, and then the data modality. So it depends what you do. So for example, Visium, the non-HD Visium, it's very clear. You have this kind of regular grid of points, and that can only be represented as lattice data. There's no way to really think about this as a point pattern because there's really no randomness in the locations. The locations are fixed. When you have this imaging-based data, well, you have some options. So you can segment this into cells and, okay, maybe make an assumption that the center of a cell is maybe a reasonable position that is of interest and maybe has a random location. That can be represented as a point pattern. Definitions to come later. If you really think about it, and this maybe has some connections to what Navid and Nicholas were talking about. The measurements you actually make in most of the imaging data analysis are actually the transcripts themselves and the locations of the transcripts in 2 or 3-dimensional space. I haven't seen a lot of this done, but you could represent these transcript locations as a point pattern and kind of do the analysis at the gene or feature level. So the interesting thing is that this segmentation can also be represented as a lattice. So you can have a regular grid, which is a lattice, but you can also have this irregular lattice. And more or less what that means is that all spatial data can be represented as a lattice. Some data can be represented as point patterns. Well, yeah, if you're able to segment into cells, say, it could be represented as an irregular lattice. But actually, because now you're segmented into cells, you can take the centers of those cells and represent it as point pattern. So it sort of depends, right? So same data set can be represented in all kind of 3 boxes here. Visium non-HD, it's very clear, and it has to be lattice. Whereas some of these more things that you're thinking about, segmentations or kind of points randomly in space, can be represented as point patterns. Okay, good. So just before I jump right into most of the lecture is going to be about kind of point patterns and then a little bit about lattice data analysis. I just wanted to talk about a few other places you see statistics, so Ahmed has covered a lot of this, and I had slides in about deconvolution, but I won't go into those statistical models because those were nicely covered. But I did want to say a few things about spatially variable features, which sometimes is of interest of its own. And then I also want to kind of point to cell-cell communication, but a very simple version of that. So I think about, at least from a statistics point of view, part of cell-cell communication is about co-localization. And a lot of these things that you can apply to lattice data, and remember all spatial data can be represented as lattice data, you can kind of formulate statistics based on co-localization. And I also wanted to remind you about this first law of geography, which Ahmed also mentioned, and also comes up in different places. If you're thinking about graphs, this also still sort of applies. And basically, it's written as everything's related, but things that are closer are more related. And you'll see this theme in many places, and you've seen it already, to be honest. Okay, good. So spatial DE, this is one of the early methods to do spatial variable gene detection or spatial variable feature detection. And it's a pretty simple standard model. It's making a normal distribution assumption. So of course, we're also thinking about how to pre-process our data such that it's somewhat normally distributed in the first place. So we're already thinking about all those steps about normalization and log scale versus linear scale to make things more normal and so on. And the model has basically, so we have these y, which is basically this lattice of data. Your y is your observations, and the x controls the actual x and y locations, or maybe x, y, and z, depending on what type of data you have. But in the model, what we do is we put in the main component of this that's maybe special or new is this covariance matrix, this sigma. And this sigma is basically introducing correlation of points which are neighbors to each other. And points that are very far from each other have a much lower correlation. And so this is all controlled, specifically in this case, by something that's a Gaussian-like filter that as the distances get large, the correlation decays. So this is just a form of Tauber's law mathematically, basically. And so the way that they do this model, okay, maybe want to talk a little bit about statistical inference, and it's fairly typical strategy that they use. They basically fit 2 models. They fit the model with the sigma, and they fit the model without the sigma. And then they compare those 2 likelihoods and form basically statistical tests based on asymptotic theory and so on that says that's probably some kind of chi-squared. And so that's how the method unfolds, basically. So it's a fairly simple model, and basically the idea is we're just tying together points that are neighbors to each other through a correlation or covariance matrix. And you'll see this sort of theme come up in many other places. Okay, so just to say, this is another paper. This is from Lucas, one of our former students in his postdoc. And I mean, what is a spatially variable gene in the first place? And I think this is interesting because there's kind of multiple senses of spatial variability. So this is this classic data set that we've seen hundreds of times, especially used for comparing methods and so on, this dorsolateral prefrontal cortex. And we have genes in here that are kind of associated with the layers of the tissue. So that's maybe an expectation. But we also have spatially variable genes that are not that. And these are more maybe immune responses and so on that happen in localized regions and so on. But these are also showing a sense of spatial variability. So there's spatial variability in kind of overall structure, but there's also spatial variability in kind of local pockets of maybe physiological processes that are happening. If we look under the hood of this, very similar, actually. We also have, in this case, instead of just a simple covariance matrix, it's a covariance matrix that's built into a Gaussian process model. But again, we have this kind of slightly different parameterization. But again, things that are close to each other are highly correlated. Things that are further apart are less correlated. We also have this scale factor. And this scale factor maybe comes up interesting and connects to some of the discussion earlier about across scales. And maybe some processes happen at some scales and other processes happen at other scales. One nice feature of this method is that they actually estimate this value per gene. And so for these examples here, you can see what the estimates are, and you can see that MOBP has kind of this larger range. I must say it's not so perfectly easy to interpret these, but you have these kind of large ones. And for me, it's difficult to know if this is larger than, yeah, and maybe it makes sense because I guess it's kind of locally around a spot that this is kind of still lower than this, and then this is the largest because it's not the largest. So I'm a little confused by the ordering of the scaling, but one thing you can see is that the ones that are highlighted here are the smaller ones. So these are these little pockets. So it maybe makes sense. I mean, you might even argue that, and we'll come back to this a little bit later, is that, well, it's hard to summarize all of this information into one number, right? Because we're summarizing this into, kind of a single scale, but actually, maybe places here have multiple scales, and there's kind of multiple axes and so on. So it's a little bit difficult, but this, at least to show that this gives you a little bit more of a readout of this idea of scale, which we'll come back to later. So I did this little experiment last night. I was kind of interested. We had this discussion about biological variability, so highly variable genes versus spatially variable genes. So I took a data set and computed this. And so the biological variability on the x-axis is this kind of, you model the gene variance relationship and kind of fit the smooth curve to it and kind of adjust for it. And kind of your biological variability is kind of the distance from the point to the fit curve, which I'm not showing you there. What you do see, and here's a Moran's eye, which again, I'll give the definition of later, but what you do see is that, well, there's quite a strong correspondence. So whether you pick your starting set of genes as highly variable or spatially variable, yeah, you're more or less on the same page with that. There are some interesting things, and this is even something I discovered last night, is that if you look at some of these are actually some of the highly expressed genes. And this set here with the triangle are actually mitochondrial genes. And so I'm plotting this one here that has this really high Moran's eye and sort of a middle biological variability. And then maybe something of biological interest that kind of sticks out from the crowd. And so here's MYL2. So I guess, again, it's the sort of pocket of local correlation. So that's maybe makes sense. But what I think is that this Moran's eye is a little bit affected by overall expression. So when you have a really high expression and maybe similar values of that high expression, it also kind of retains a high value, and some of these stick out, and you notice that there's kind of a collection of genes that stick out. And so, I mean, there's kind of some biases in all this. So this is very quick and dirty, so I feel like I need to come back to it and understand it a bit more, but I thought it might be interesting given the discussion that we had. Okay, so just to talk about maybe yet another sense of spatially variable, and this is something that a postdoc in our group, who's now left, led, Simone Tiberi. And we had the idea that, well, actually, a lot of what we think of in terms of spatial variable is really just represented by the clusters that you have. So what if you take a data set, cluster it, look for the differentially expressed genes? That readout of the differential expression is actually very similar to a readout of a global spatial variable. Now, I mean, I think that's nice to know. And if you're interested in some of these kind of more subtle, more localized things, we can find these also, but it requires subclustering, which also kind of makes sense. So if you do kind of a higher resolution clustering, then you can start to see some of these smaller patterns. So I mean, just to say that spatially variable, you can express it in Moran's eye, you can express it with these nice models that have correlation built into the model, or you can just do differential expression. And that was kind of the point of this. And at least this is integrated nicely into pipelines and super quick to compute. Well, I mean, assuming the clustering algorithm doesn't take that long. But in addition to clusters, the computation here is really tiny because this is kind of standard pseudo-bulk differential expression kind of things. Okay, so we're coming back to this. And you know now that we can kind of subdivide the data that we have into point patterns and lattice data analysis. So I'm going to focus a bit on point patterns. And yeah, if people are interested, there's kind of a free online textbook for this. So what are point patterns? So it's data with spatial locations. And you're thinking about that those locations are kind of originating from a random process. So there's some randomness in the location of the points that you get. Okay, and there's quite a clear separation with lattice data. Lattice data, you were thinking of, or you're representing your data as kind of fixed locations, whether that's a grid according to the technology, or if it's based on segmentation and just having an irregular lattice. Yeah, so and we also have kind of tools that give analyses about discrete and continuous marks. So each of these points has a mark. That mark could be a cell type, it could be gene expression, and so on. We'll come back to that a bit later. We mostly focus on the discrete, but they're in the tutorial there is some analysis of continuous. Okay, so again, thought experiment. There's 3 examples here. Take a minute to read those, and then just think, okay, is this a point pattern or not? Okay, 14.1, hands up for point pattern. So the trick is that it's in this word fixed. A weather map for Europe displays whether a major city indicating expected type of weather. Are those cities fixed locations? Or are they random locations? I hope they're not random. They're fixed. So that is definitely not a point pattern. Trees in let's skip to the last one. Trees in an orchard are examined and their disease status. We are interested in the spatial characteristics of the disease, such as contagion between neighboring trees. So this is the kind of thinking. So I mean, I think there's some uncertainty, and that's why they're good examples. I think in this example, because we're talking about the location of the diseased trees, that is in random. It could, however, be that you have an orchard and things are planted in rows and kind of perfectly and so on. So it's a little bit unclear. The one in the middle, sky position of each galaxy. Yeah, okay. So it's this one could be easily called, but you can also see that it's not so easy to fully decide on this. Okay, so I'll go into some definitions. I won't belabor this too much, but basically, yes, you have some points, and what is important is a so-called intensity function, lambda, and you can integrate over this for a given region, and then you can start thinking about the number of points that fall within that region. And that, because it's a random process, the region is a certain size, it's a random variable of how many points would fall in some region of a given size. And so, yeah, this is also closely linked to Poisson processes and Poisson models. The basic model is Poisson. A few more definitions. Homogeneity. The points have no preference for any spatial location. So that's maybe thinking about surveying cells. Cells are located in some kind of space. Are they homogeneous? Meaning that the density of cells is fairly constant throughout the space. That's really what homogeneity is about. Independence. Do the points influence each other? There's another definition of this, I think it's maybe down below, that has to do with, well, if you have a region A and a region B and they're disjoint, are those 2 random variables independent of each other? So again, coming back to fairly standard basic concepts. Yeah, so we're kind of just laying the foundation here. Just to say this maybe a bit more, there's also a so-called inhomogeneous Poisson process, which has an intensity function. I think the example that was mentioned here, if you have a constant lambda, that is homogeneity. So you have a constant density of points. So this comes up a little bit later. Independence has to do about these non-overlapping regions, whether the random variables associated with those regions are independent or not. And I mentioned this Poisson distributed count. So basically, does the number of points given a region, is it a Poisson distributed random variable that's kind of proportional to the size of that region? Okay, so let's look at 3 point patterns now. Okay, let's start with row number 2. I'll give you a hint. The answer is that only one of these is completely spatially random. Unanimous, number 2. So this is completely spatially random. Which of these is not independent? So independent has to do about maybe interactions between the points. Which of these is not? So basically, the one on the left is not independent. And the reason is it's too regular. Points are repelling each other. So it's anti-clustered. It's whereas you can kind of accept that there's clustering on this one. So let's now talk about homogeneous. The first one and the third one are not independent, but the dependence is the opposite, right? So one is repelling, one is attracting, but they're definitely not independent. Whereas the one in the center is independent, just by nature of what a Poisson or a completely spatial random process is. And yeah, I mean, basically, in order to generate this, you just generate random numbers on the x-axis and the y-axis, plot them down. That's what you will see, more or less. Whereas processes like this have a very specific additional component to it that make it not independent. Okay, so we talked about independence. What about homogeneity? So what's interesting here, and maybe even counterintuitive, is that they're all homogeneous. So the intensity of points is flat. It's a constant. It may not look like it because of this clustering structure, but the clustering, again, is this additional component. In terms of the space and the density, it is, because it's generated that way, it is homogeneous, but it's also really good that you're puzzled about this because it comes back later. There's a little bit of a problem with. Okay, so just to say that there's lots of extensions to this. We're not always talking about points. We can talk about lines. We can do some things in higher dimensions. We can have temporal components. That's kind of a big sub-area of statistics. I do want to mention a couple things. I mentioned this already, this concept of mark, and that's important for us, of course. So if we have these points, which we're typically representing as cells, that is going to typically have mark associated with it. And a mark can be a continuous thing, like gene expression, or a discrete thing, like a cell type, for example. We also have so-called multi-type point process. I think I have an example of this. So this is basically this is from John Marioni's group. Basically, a multi-type point process is basically a process that has multiple types. And there's actually, I'm going to ignore this little subtlety here, but there's a few different ways to model this. You can model it as a multivariate process, or you can do the simpler thing, which is what we mostly do, and just focus on one cell type and think about a process that's just that one cell type, or maybe just a pair of cell types if you're looking at interactions between them. Okay, so there's some terminology and definitions. Okay, so let's talk about the first thing that you might have heard of already, a Ripley's K function. So in words, the word definition is, it's an empirical function. It's a cumulative average number of points lying within a distance of r of a typical point. So take a point, put a radius r around that point, and then do that for all points and average the number of points you see within that r radius. And then take that radius and do across scales from low radius to high radius. And so that's why this is cumulative. It's always increasing. And basically, here's a radius of these particular points, and here you can see these 3 different lines, and you can see the independent or the completely spatial random process is in the middle. When you have this what I'm calling regular is this kind of repulsion of points. Within an R radius of any point, you have fewer points, right? Because they're pushing each other away. And then the clustered one is higher. And so this gives you a bit of a readout and a quantitative readout across scales of some feature. And this is a typical feature that people would look at, correlation. Okay, so here's the kind of the technical definition. So it's basically kind of a indicator function and so on. There's a few details about whether it's a stationary process or so on. I will kind of skip over that. I will come back to this kind of construction of the function later when we talk about some other conflicting issues, which are things like edge effects and this inhomogeneity that we've talked a little bit about. Okay, yeah, here we go. So what happens when you do have something that's not homogeneous? So you have two options. You can assume homogeneity and compute these functions, or you can assume inhomogeneity and kind of correct for it. I won't go into all the details of this formula, but what you can see is you're also kind of scoring these R neighbors, so between 2 points. You're dividing by lambdas, so the kind of the densities, local densities of the two different spots. So you're kind of accounting for the local density. And then you have this term over here, it has to do with edge effects. So all of these have a lot to unpack, and I'm not going to unpack it all here. And actually, in terms of edge effects, I barely understand what they're doing, other than the fact that points near the edge need a little compensation because you're not even able to extend an R radius around the points. So there's kind of but there's different ways to do that and so on. But just to give you the idea that, well, you can assume homogeneity and compute the K function, or you can compute an inhomogeneous function that in the calculation compensates for some of this this inhomogeneity. Okay, so I think it's already getting sufficiently tricky, and so let's talk about maybe the key issue with some of this that you may come across. And so here I'm showing you a few point patterns of a given cell type, and what I'm doing is I'm kind of coloring these points according to a local density. You can kind of see that. And this is one of our examples in the paper, and this is so-called confounding between clustering and intensity. So clustering is a little bit related to the term correlation. And the idea is that if you calculate a standard K function, so you're assuming homogeneity, so assuming the thing is flat, then you get these curves that jump above the dashed line, and the dashed line is a Poisson, that's completely spatially random. However, if you account for it and calculate an inhomogeneous function, you get curves that are kind of fairly close to random, meaning that, well, it kind of begs the question, is this a change in intensity, so via the intensity function, or is it a change in correlation of the points? And that's actually a somewhat difficult thing to differentiate in these models. So that's just something to be aware of. I mean, I think where we're going with this is that there's not just the K function, there's other functions, and in relative terms, like kind of the differences between these functions, there's maybe some quantitative information in those and so on. But just to point out that even in the statistics field, this is already a bit of a gotcha, that there is this confounding between intensity and clustering. And I think it actually nicely came up in the discussion. So I mean, I don't have a kind of a solution for this. It sort of depends on the situation that you're kind of applying these methods to. Okay, and I just wanted to say that, so yeah, I mean, I guess we have these, if you're thinking of an R radius, you can also do local versions of this. And we'll come back to this a bit later with kind of the Moran's eye and local versions of those and so on. But the idea is that basically you can compute this average over all points and get kind of a single summary of the kind of the correlation in a data set. But you can also do a single curve for every point. And I've colored these points according to what happens at a radius of 200. So we're getting information about scale here. And the points that have a lot of points around here are ones that are the denser regions. So this is just a kind of a direct readout. The reason I wanted to kind of highlight this is that sometimes we, at least in spatial statistics, and this was also hinted to by Navid, where he had these kind of spatial metrics that are curve across scales, and also in Anna's talk, there might be situations where you have lots of curves. And so maybe a natural thing to think about digesting this a bit is actually a so-called functional PCA. So another subfield of statistics is called functional data analysis. And the idea is that instead of individual numbers, you have curves. You have a functional response, for example. And what you can do is you can take all of these curves and you can compute a functional principal components. And for these set of curves, it's perhaps not surprising that you have kind of this one axis, your pre-C1, that kind of represents the density because it's kind of representing the structure. Unfortunately, in the software, I had a difficult time because it kind of decomposes the mean curve and then deviations from the mean curve as you go across the different principal components. I wasn't able to fully pull out what exactly I wanted, but at least visually, you can see that the first principal component is representing kind of the axis or the deviation from the mean that really represents density here. And this is a case where we probably don't need anything more sophisticated like nonlinear because most of the variation in these curves, because they're a bit constrained to be always increasing, there's not so much variation to explain and so on. So you can do this quite easily with kind of simple methods. Okay, so that's just a little bit of a side note, but I will come back to that later to say that, well, these curves can be quite useful for maybe larger experiments when you have maybe multiple measurements per patient and multiple patients and experimental conditions. You can start using these curves as your kind of your summarized data to do this. This is just showing you yet another curve, basically looking at nearest neighbor distances. So for each of these 3-point patterns, according to the different colors here, I'm computing the distribution of distances to the 5th nearest neighbor, which is a somewhat arbitrary choice. But what you can see is that the distance to the 5th nearest neighbor here is always quite low. You have this kind of peak here. For microglia cells, much more spread out, so the distances are much larger. And OD mature cells is interesting because you have a bit of a mix. You have things that are spread out, but you have also these dense regions. And so you have a bit of like a bimodal distribution here. And so the point I'm trying to make here is that, well, I've talked about K functions. This is another curve of a certain type. But in the end, there's actually lots of other curves. I think I have a slide here. So here's kind of a list of the set of curves. And you may think about designing a curve to summarize a spatial property, some property of spatial homogeneity for your situation. So there's some options available here. Okay, I think I will skip over that in the interest of time. Jump on to lattice data because there's a little bit less to say about lattice data when you have lattice data. And remember, all spatial data sets can be represented as lattice. You don't have as many options available to you. You're mostly kind of constrained to things like autocorrelation, which we've discussed a little bit. Just want to discuss a few options of this. Okay, so definition-wise, lattice data is basically these areas of a space that are non-overlapping. And you have some random variable measured on that lattice. So this is your gene expression, for example. Yeah, spatial units have the same size, shape. Yeah, that's for the regular lattice. You can also extend this a little bit for the irregular lattice, maybe needing to make some compensation for cell size and so on. And like I said, the main thing that you're able to do with lattice data is some kind of an autocorrelation. And I want to represent this in a very generic way because this representation relates to all of the things that you probably already know about spatial autocorrelation. And so basically, all of these spatial autocorrelations have basically a form like this where you have a weight and you have some similarity measure. And I'll show you a few different versions of this similarity measure. And also show you a few different versions of the weights, which was also discussed a little bit this morning. You have a graph, you have weights. You have nearest neighbors, you maybe have weights, and so on. So there's a few different ways to construct this. But you can also kind of pair these together in a somewhat flexible fashion. Okay, good. So Moran's I and Geary's C, you can think of these as, again, these are functions that have that standard form. They have the weight, and then they have some kind of similarity metric, which in the first case, yeah, actually in both these cases, although it's kind of expressed a bit differently, is some kind of relationship to correlation or, yeah, relatedness. And also to say that there's local versions of this. And so coming back to our standard form here, you have a weight and a mu. You can calculate these for individual locations and have the local version, or you can kind of sum them up, and that's your kind of global version. So that's more or less all you have. And what I want to say is just a few different versions of this. So your local Moran's I. So here's the gene expression level. Here's the local Moran's I. And you can compute a p-value for every location. OK, it's a little bit of an extreme case because you probably have a multiple testing correction and so on. But you can kind of do this in a global scale and do statistical testing on a global scale, or you can do this at the local level. OK. I just want to say, and this is something that comes up in the tutorial, the weight matrix that goes into all of these scores. And then we had a little bit of this discussion earlier. Here I just pulled out 3 different possibilities for the weight matrix for the data set that you'll be working with. And also to say that the Museum of Spatial Transcriptomics paper was mentioned, and also Lior has this package called Voyageur, which actually does a lot of this computations in R, and so our vignette also uses a lot of those tools. But just as a visual readout of this data set, yeah, you have your regular grid. This is a Visium non-HD data set. And so if you look at the adjacent neighbors of that, you can form a weight matrix based on those, in this case, equal weights to all of them. You can also do the H&E neighbors. So you have, for this particular slice, you have an H&E stain, and you can segment that into individual cells and kind of get an idea of the connectivity of different cells and propagate that up to the spots and use that as your weight matrix. Or you can use different nearest neighbors as your weight matrix. So just to say that you have many choices, it has subtle effects on some of these computations, which could be important in some situations. It probably won't have too much an effect on the global values because it's kind of averaged over all points, and there's typically lots of points. Okay, and then just to extend this one step further, again, another function that has weights and has a component here. And in this case, this component includes an x and a y. So this is your Moran's R that allows you to score co-localization. This is from this spatial, or at least the concept of it is from the spatial DM paper. And the schematic here is showing you a ligand and a receptor. The ligand has this kind of horizontal hash. The receptor has this vertical hash. And in this case, they're not really co-localized. You can see the horizontal and the vertical hashes are in different positions. So this would receive probably a fairly low Moran's R, whereas in this particular example, these are kind of co-localization. So it's a quick and maybe dirty way to score co-localization of 2 molecules, which could be useful for ligands receptors. But this can also be done in a local way or in a global way, as you've seen. So it's kind of a general framework for all of these. And yeah, I mean, technically you can design a different U function to have spatial similarity of interest. Okay. Any questions? I have one short segment that I want to tell you about, just to tell you a little bit where this is all going. Any questions I can answer? Lattice data analysis. Yeah, there's limits to what you can do there. There's less available, and these are kind of the standard things that are available to you. Okay, good. So last segment is what I hinted to before, and that is where is this all going? So where is this potentially useful? And the idea is that we're thinking of downstream analyses here. We're thinking of larger experiments where you have maybe a cohort, you have patients. Maybe in some cases you have patients where you're taking multiple measurements from. And the idea of this framework is that, well, these curves may be useful to quantify some spatial feature of interest, but we have lots of curves. So to give you an example, so this is the biological example here is islets, and you have these alpha cells and beta cells. And in diabetes, essentially, your alpha cells are kind of, it's the beta cells that get progressively destroyed. And so you're seeing less and less of those. So, I mean, honestly, for this particular problem, you can quantify just the abundance of beta cells and you get a similar readout. But in terms of spatial representation, it's about alpha and beta cells in these islets. And so that's what we chose to score. We have this kind of G cross function, which was mentioned in our list before. Well, there's the G inhomogeneous. this one here, nearest neighbor distance function. So it's basically looking at the neighbor, the distance to the neighbors, essentially, of alpha and beta cells. So that's essentially what we can quantify. I'll come back to that in a second. Here's our experiment. So we have 12 patients from three different experimental conditions or kind of subgroups. So we have basically the non-diabetic patients. We have early onset patients, and we have long duration patients. And the way that this experiment was constructed is that we take multiple fields of view for one patient. And that's partly because this was an IMC and the regions which you can profile are quite small. So they kind of made multiple measurements per patient. That structure could be important, actually, because you're sampling multiple times from the same patient. They're not independent kind of observations. So you can't just throw them into your classical models and say, yeah, these are independent observations. I've got this massive sample size. These are all measurements from the same patient. There's a correlation built in kind of by nature there. Here we're quantifying G cross. And you can start a little bit to see that, well, the distances are maybe a little bit more increased in the onset, but it's actually quite noisy, right? There's a lot of variability here. And so the idea is that, we can take a lot of data and represent them as quite simple functions and simple functions that have a scale to it. So there's maybe a little bit of an interpretation you can make in terms of scale. And so, yeah, so the idea, this is just a kind of a schematic of the experiment. We have these multiple patients per subgroup and then multiple fields of view per patient. So we want to build in all the structure. I won't go into all the details here. Here's your kind of your simple functional PCA analysis of this. You can see a little bit of a separation, especially of this onset group. What we propose, and we've been studying and trying to demonstrate the sensitivity of, and this is in the spatial FDA package that Martin developed, is that we treat this as our response. So of course, we have a lot of steps to get to this point and kind of compress our data into this set of curves. But now we think of these curves, and that's our response. So we have this kind of functional additive mix model. The additive mix part is really just kind of allowing us flexibility to build in the correlations of making multiple measurements from the same patients and so on. And we have a fairly typical model set up, except that everything here is functions as opposed to kind of single observations. So the idea is that, yeah, we have an intercept term, but the intercept is a function. And we have a regression parameter that maybe represents the difference between, say, the early onset group and the long duration group. But that's not a single number. That's also a function. So our parameters are also functions, and we do inference on the function. So I don't want to belabor all of this. There's much more details to unpack, but just to say that this is where this is going. And basically, this is just to say, here we're actually doing formal testing, and there's some mathematical details about how we form these error bands and so on. But essentially, what we can see is we can see at a certain range, we can see a difference in these curves, which represents an interpretation of a change in spatial heterogeneity. And we sort of saw this in the curves, but here we a little bit more formally nail this down and allows us to do a testing framework for this. Okay, so that's just a kind of a snapshot of where we're going. There's, lots of other work in this space. I'll just have a couple concluding remarks, and just to say that what you learned is that we have kind of two different streams. We have lattice data, we have point pattern data. We have different options for those. We even have different options for the same data sets, depending on how we want to represent it. Most of the point pattern work relies on these functions, these summary functions. And that can be your classical K function and so on. But it can also be various other types of functions. And we've seen also in the other talks, we have these functions that have scales, and well, eventually maybe these functions can be compared to each other and so on. So kind of thinking of the function as the response.